Hello friends, I welcome you in lecture number 11 on complex differentiation. In previous lecture we have understood the meaning of analytic function, and now we know that if we have some function say f of z, then it is analytic at some point z0 if there exists a circle with center z0 and with some radius say r, such that function is differentiable at every point inside that circle, and the set of all points inside the circle is called neighborhood of point z0. So function f of z is analytic at point z0 if there exists some neighborhood of z0 such that f of z is differentiable everywhere in that neighborhood. So as we have discussed in earlier lecture that if our function is differentiable at every point, then it is always analytic at every point. Similarly, if function is not differentiable at any point, or if function is nowhere differentiable, then function is nowhere analytic. And we have also discussed that if function is differentiable at finite number of points, then also it cannot be analytic at any point. So we can remember these simple remarks that will be helpful for us to determine the analyticity of a given function. So we will remember all these remarks. A function which is differentiable everywhere is analytic everywhere. Similarly, a function which is nowhere differentiable is nowhere analytic. And if a function is differentiable at finite number of points only, then it is nowhere analytic. But it does not mean that if function is differentiable at infinite number of points, then it is analytic. We can have a function which is differentiable at infinite number of points and it cannot be analytic at any point. If you have watched my earlier lectures, then we have discussed the differentiability of this function f of z equal to x square plus iy square, and we have proved that this function is differentiable at all points on the line y equal to x only. So this function is differentiable at infinite number of points which are on the line y equal to x, but we know that it is not analytic at any point on the line as well as at any point outside the line. And this we have discussed in previous lecture also, that this function is differentiable at infinite number of points on the line y equal to x, but it is nowhere analytic. So we will remember all these remarks related to analytic function, and that will be helpful to determine the points at which given function is analytic. So with all these things in our mind, we will discuss some problems in which we will check whether given function is analytic at a given point, or we will determine the number of points at which given function is analytic. So in this lecture I have taken this function f of z equal to z cube, and I have to determine the number of points at which this function is analytic, or they can ask in this way also, discuss the analyticity of the function f of z equal to z cube. Now we know that first we have to decide the differentiability of this function, and once we decide the differentiability, then we can check whether function is analytic or not. So for differentiability, if you have seen earlier lectures, we are using Cauchy-Riemann equations. We determine the number of points at which Cauchy-Riemann equations are satisfied, and for that first we express our function in this form u plus iv, that is u is real part of f of z and v is imaginary part of f of z, and for that we consider z equal to x plus iy in the formula of given function, and after simplification we will be able to write our function in this form. So I have written all these steps for this function. I start by taking z equal to x plus iy here, and then I will expand using the formula of cube of a plus b, that is valid here also. Here we know that this is given by this formula. So for this we will consider a equal to x and b equal to I into y. So a cube means cube of x, b cube that is cube of I into y, that is I cube y cube, then 3 into a square, 3 into a equal to x, that is x square, into b, b is iy, then 3 into a into b square, a is x here and b is iy, so square of iy is I square into y square. Then we know that I square is minus 1, therefore I cube will be equal to minus I, that I have written here, and here I replace this I square by minus 1. After that I combine those terms in which I is absent, so they are x cube and minus 3xy square, and from these two terms I take I common and I first write 3x square y and minus sign y cube. Now this is in u plus iv form, so we compare with u plus iv and we find that u is x cube minus 3xy square and v equal to 3x square y minus y cube. After this step we have to determine the first order partial derivatives of u and v with respect to x and y. If we differentiate this with respect to x, we will have 3 times x square minus, here we are differentiating with respect to x, so y is constant and therefore y square is also constant and derivative of x is 1. So del u by del x will be 3x square minus 3y square, and that I have written here. And when we differentiate with respect to y, we consider x as constant, therefore x cube is constant, and here minus 3x is constant, derivative of y square is 2y, so we will get del u by del y equal to minus 6 times x into y. Same thing here, first we differentiate with respect to x, therefore we consider 3y as constant, derivative of x square is 2x, so we will have 2 into 3, that is 6 into xy. And when we differentiate with respect to y, we consider x as constant, so 3x square is constant, derivative of y is 1 minus derivative of y cube is 3y square. Once we determine the derivatives, we find out the points for which these two equations are satisfied. Ux equal to vy, and second equation was del u by del y equal to minus del v by del x. Here we can see that in del u by del x and in del v by del y, right hand side is same. That means this equation or these two functions are equal at every point in the complex plane. Similarly, we can see that here del u by del y is minus 6xy, and if we take negative sign here on both sides, then we will have minus 6xy here. So del u by del y is minus 6xy, minus del v by del x is also minus 6xy. That means these two functions are equal at every point in the complex plane. Therefore, both the equations are satisfied at every point in the complex plane. So that I have written here clearly, ux equal to vy and uy equal to minus vx at every point z equal to xy. That means Cauchy-Riemann equations are satisfied at every point in the complex plane, and all these first order partial derivatives are polynomial functions. Therefore all these first order partial derivatives are continuous at every point, so that also we have to mention. Also ux, uy, vx, vy are continuous at every point z equal to xy. So both the conditions of differentiability are satisfied at every point z equal to xy. Therefore, function is differentiable at every point z equal to xy. And we know that if function is differentiable everywhere, then it is analytic everywhere. Therefore, f of z equal to z cube is analytic at every point z equal to xy. Or in other words, we can say that f of z equal to z cube is analytic everywhere. We know that if function is differentiable at every point in the complex plane, then if I want to check analyticity at this point, then I require neighborhood of this point such that function is differentiable at every point in that neighborhood. But function is differentiable everywhere, therefore it is differentiable in any neighborhood of any point. Therefore, definition of analytic function is satisfied. So whenever we have our function which is differentiable everywhere, then we can directly write that function is analytic everywhere. So this is one example of analytic function. You can check for different functions of this form. You can try for different functions in this form where n is a natural number. We have shown in earlier lectures that f of z equal to z square is differentiable everywhere, therefore it is also analytic everywhere. In general, if we have this power of z is positive integer, then this function is always analytic everywhere. In fact, if we have any polynomial function, then also it is analytic everywhere. You can prove that polynomial function in this form is analytic everywhere. Now the functions which are analytic everywhere or which are analytic at every point in the complex plane are given name as entire function. Entire function means that type of function which is analytic at every point in the complex plane. And now we know that f of z equal to z raised to n, where n is positive integer. This is analytic everywhere, therefore this is entire function. Sometimes they can ask you to prove that f of z equal to z cube is entire function. So in that case you have to show that function is analytic everywhere and therefore it is entire function. Sometimes they ask you to write down the definition also. A function which is analytic at every point in the complex plane is called an entire function. So this is all about this session. We will continue with this type of problems in upcoming lectures. Thanks for watching.